Hi, everybody. Thanks for joining this webinar today. We're going to get going in just a few minutes, give folks a few more seconds to file in. To get us started, if people want to just drop in the chat where they're joining from, we can get a little community going. All right, great. Looks like global audience joining us today. We'd love to see that. We can go ahead and get started. Once again, thanks everyone for joining. My name's Dan Kane. I'm the Director of Partnerships here for Onshape. Onshape, for those who are new, is the global leader in cloud-native CAD and PDM. And one of our sort of core tenets as a product and a company is openness and innovation. And we love to provide open platforms for other technology leaders to build integrations and add-ins to the Onshape platform that extend the capabilities of Onshape beyond just CAD and PDM into some really interesting areas as a part of engineering and design workflows. Really excited about particularly today's session with Luminary Cloud, who is indeed a technology leader. I'm really excited for everyone to be able to see what they've built on their own, and then also how they've connected it with Onshape to help augment everyone's workflows. So with that, I'll kick it over to the Luminary team to introduce yourselves and kick us off.
Yeah, sure. Hi, Robert Coyote. Really happy to be talking to you all today and talk about what we've built here alongside Onshape. I'm a computational engineer at Luminary Cloud. I did the primary work on actually building this integration and rolling it out to customers. And we're really excited to show you what we've been doing.
Hi, everyone. I'm Joseph Warner. So I lead product marketing here at Luminary. And yeah, excited to talk about our work with Onshape. Great to be here. All right. Cool. So I think we can go ahead and jump into it. Yeah, so today we'll be talking about how physics AI is actually reshaping and redefining the relationship between simulation and design. And so I'll kind of talk through some background information, and then I'll hand it over to Rob to talk about our integration with Onshape and some of the exciting work we've been doing. Cool. So just looking at the high-level agenda, we'll start with just an overview of Luminary. Again, I'll hand it over to Rob to talk about our integration, and then we'll talk about our shift wing model, which is really interesting. It's a pre-trained physics AI model, and I'll let Rob go into the details on that. And then finally, physics AI inference. So we're actually going to show an AI model doing inference on the actual physics of this particular set of designs. And so again, very exciting. And Rob's going to show a demo of that. Okay, so let's jump into Luminary overview. So there's an interesting thesis here, and it's a bit controversial in some sense, but our thesis is that engineering simulation actually can slow product development, right? So when you take a design, you need to evaluate that design. And there, you can do testing, of course, but the most common way to evaluate design is to do simulation. And that requires you to go through this very manual, slow process from geometry to meshing to actually running a solver, right? And so each of these can take a lot of time, a lot of manual effort, and then you evaluate that design based on the simulation results and you iterate. And this whole process can take days or even weeks, depending on the complexity of the particular simulation. And this applies across a variety of industries. So automotive, aerospace, electronics and semiconductor, HVAC, and industrial machinery. And so what we're seeing across industries right now is that physics AI is actually reshaping this process, right? So we can take a design, and with the physics AI model, we predict in seconds, or sometimes less than a second, the actual full simulation results with high accuracy. And we'll get into the details of that a bit more. But I think the important thing here is that we actually can remove these manual time-consuming steps. So you don't need to do this typical computational meshing process, which is very manual and iterative and time-consuming. And then when you go to solve, you're not doing traditional numerical solving, which can take hours or longer. You're actually doing inference, and so it's very quick, and then very repeatable and robust. And this opens up some really interesting use cases. So things like rapid design iteration, which is particularly relevant for people who work in CAD tools, for example, working in Onshape. You can actually do inference and very quickly get feedback on your design as you make changes. But of course, also design exploration. So we can fire off a number of different inferences across various configurations and evaluate them all at the same time. And then optimization. So actually wrapping this process in some sort of optimization algorithm and driving towards some best design automatically. And then finally, digital twins. So how do you take these models and use them once the product has been deployed in the field, and use the inference to evaluate the performance of very quickly and and cost effectively as well, right? And so all of these things, they're traditionally possible with simulation, but they are really unlocked, and you're able to do them at much greater scale with physics AI. But there's a bit of a catch here. So what we've seen is that data is the bottleneck, right? So people have tried to build these models, and they would typically train the model on, say, 100 simulations is typical guidance. And what we've seen is that's just not nearly enough data. And it kind of makes intuitive sense as an engineer, right? So we have this quote from Neil Ashton, who's the distinguished product architect of CA at NVIDIA. And he kind of says physics AI models are essential for real-time interactive engineering analysis and design, but they just require tremendous amounts of data, right? And so we'll talk about what Luminary is kind of doing to address this problem. What we've built is a unified physics AI platform from data generation with our GPU native solver to model training, and then actually deploying inference in your production environment, or you can use our APIs, and we'll talk about that a bit more. But we also have access to our pre-trained shift models, and Rob's going to talk about that. So what these models allow you to do is actually kind of bootstrap, if you will, your process. So you can take a model and actually fine tune it such that you don't need as much data. You don't need to bring as much data yourself to get started and get high accuracy results, so that you can use it for engineering grade analysis and design. And then finally, other data sources. So you may have experimental data or test data that you want to bring in and train the model on and help ground it in the actual reality that you've tested. So to dig into this a little bit more, so what we actually have here is we call it our physics AI factory, right? And so all of this exists within the Luminary platform, from data generation, geometries, meshing, and our GPU native solvers, which run, of course, simulations very, very quickly and cost effectively. All this data is fully managed within the platform, along with our shift models. And then you're able to train models all within the platform with a very robust and extensive API SDK. We also have an MCP server and an AI assistant, so you don't have to be an expert in our SDK to get started. I think Rob's going to talk about that a bit more. And you access all these things through our various interfaces, from our browser-based UI to our SDK and our in-app notebook as well. So we make it very accessible, but also extremely powerful, and it's all fully managed such that you don't have to go and piece all these pieces together, because we often hear that customers are trying to get started with this area, but it's quite challenging to piece all these things together yourself. Right, I'll hand you over to Rob. Thanks, Rob.
Yeah, sure thing. Thank you. So now we'll talk a bit about this Onshape integration that we've actually built, and how kind of we're working with Onshape to make a very powerful connection between Luminary's capabilities and Onshape's world-class CAD platform. So as Joe just pointed out, physics AI is reshaping engineering design, but as we removed simulation from this inner loop, we need to really tightly couple this design prediction loop now to actually get those benefits. And that what really lets us power these things is by connecting with CAD companies, especially ones in the cloud like Onshape, where really they are the world-class leader here for cloud native CAD. So this allows you to do things like rapid design iteration, which we'll show a little bit about today, design exploration through having parameterized CAD that Onshape enables, optimization, which we've done before but won't be talking about too much today, but really just kind of enables all these workflows we were talking about before by having this tight coupling, which we built through this integration. And the reason this works so well is really because there's quite a bit of synergy between Luminary and Onshape. So first of all, we're both cloud native, and this means that both platforms you can expose. You don't need to worry about talking to your IT department and getting access to install things. If they allow you to access this website, you're good to go basically from there. And also you ensure seamless, scalable, and accessible workflows. No matter where you are for your entire team, you can collaborate together, even if you live on different continents. You can quickly share products. You don't need to worry about, how do I send this file over? Let me zip it and put it in Dropbox or something. Instead, you can just send a link and we're already there. You can share with access controls, all those kinds of things that both of these Onshape and Luminary enable. We also have robust and open APIs. And this means that if, for instance, what I showed today in our integration is not exactly what you need from either the Onshape part or the Luminary part, both of us have very flexible and open APIs that you can actually use to customize this to your exact workflow that you need and really power exactly what's going to help you and your company get your work done. We also discussed 4 rapid design exploration, and that's really made possible by the fact that Onshape is very, very good at robust CAD generation, especially if you make parameterized CAD either through configurations or variable studios. And then this can, with the integration, be directly imported into Luminary and tracked with version history for design sweeps and optimization at scale. And again, this is made possible by the fact we're both in the cloud. And lastly, both of us just live on the cutting edge. So you can be confident if you're working with Onshape and Luminary that you're going to be at the forefront of what's being done in both the CAD and simulation, CAE, physics AI worlds. And you'll know that we'll be good taken care of and you won't be falling behind against your competitors. So now we're just going to show really quickly what the integration does, just the bare bones of it. There's a bit more to it as well. We're just going to show kind of the key functionalities. So essentially here, we're starting from Onshape. This is the shift wing model that Joe mentioned. We're going to talk a bit more about in a couple minutes. But essentially, it's a parameterized model, has quite a few parameters in the variable studio, as you can see. They're actually controlling what the shape of the wings look like, how they connect to the fuselage, the shape of the fuselage itself. So essentially, we're in Onshape. Now we'll switch over to Luminary. All you need to do with this integration is go to your settings in Luminary if you have an active Luminary account, click Connect Account for Onshape, and there we actually performed an OAuth workflow. So we were already signed into Onshape, so that happened very quickly. Otherwise, you just sign into your account. So now we're just going to start a project in Luminary to kind of track our work that we're going to be doing. Now we're just going to upload a file like you do normally, and you can see there's an Onshape button. And what happens is we're actually pulling and showing all the documents you have in Onshape. So these are just the 8 most recent or so. And then we can actually view in that both versions and workspaces. So here we have the main workspace. We have our starting version as Onshape creates when you copy a workspace, and also just one I called Perfect that I made up just to show that we can actually track these user versions. So inside each one of those, you saw we have part studios. We can also import assemblies as well, and also subsets of parts from those. So when we perform this import, essentially what we're going to do is we make, as you can see there, a new version. And this kind of lets you track in your history in Onshape what the state was when you imported it into Luminary. And then that's actually going to perform an export in Parasolid, just a technical detail, from Onshape into Luminary. And this is all real time, by the way. So that is how quick that happened. And the really cool part is we're also pulling in that variable studio information that I showed before. And even cooler, we actually maintain that connection between Onshape and Luminary. So you can now go ahead in Luminary and change, for instance, the aspect ratio, just because it's a really visual one that's easy to see. Click apply, and we're going to go back to Onshape and make a change in that variable studio and re-import that changed geometry. So this allows you to, from inside Luminary, to leverage a lot of the really cool things about Onshape once you've set up something like a parameterized CAD and maintain that robust connection between the two. So you'll see we're performing that import just like we did before. After a few minutes, you'll see that we have a very strange looking plane, and that's because we just made a large change to aspect ratio, so you can very easily see that we did actually import a new geometry. So here we're just doing a couple light checks. We have Luminary, and now you can see this new geometry. So we never had to go back to Onshape to do this, to kind of drive this feature. So that means if you have a CAD you want to explore that's parameterized, you can do a lot of that from Luminary and actually get that scalability and optimization loops we were talking about before. And then if you have all those variables, we also have search functionality and those kinds of things to help as well. So now we're going to do something a bit weird, but we're going to make a branch from our import just for reasons to make a branch. And we're going to name it broken branch because we're going to purposely break the Onshape regeneration. And the point here is we will demonstrate how we also kind of keep that connection and how it actually has multiple benefits beyond just being able to change variables. So like I said, we're purposely going to break this. We'll generate 2 warnings in Onshape. We'll then swap files. So this is basically going to import a different Onshape part studio because we're going to switch from importing the main workspace to importing the broken branch workspace we just created. You can see this document browser already updated because we're keeping that connection to Onshape. And once again, it's all authenticated against your own account. So you're only seeing the things you can see and you have access to, but if people share Onshape documents with you, you'll be able to see them in Luminary as well. So the key thing here, though, is as I said, we made that break in the regeneration. So we got some warnings in Onshape. And what you'll see is we're doing this import. We did a branch from our originals. We're going to go back to our original aspect ratio of 12. Plane looks more normal. But the key thing here is we're actually propagating these errors forward into Luminary. So if you're making these changes in Luminary, for instance, and actually accidentally break the regeneration in Onshape, you'll be made aware of that. You won't just be importing ghost parts because we don't have the fact that we actually broke something in Onshape. So this just kind of shows, again, the connectivity that we can actually build and inspire in both of these. And the last thing we're going to demonstrate is kind of something central to Luminary's SDK and scaling ability, which is the ability to import metadata from CAD, which we refer to as tags. But in Onshape, it's actually done by assigning face appearances, just because that's the way it comes through in Parasolid. So what we're going to do is first make a mistake in the recording and realize I need to go back because I don't want to have a broken state anymore. So we'll take advantage of Onshape's very nice Control-Z capabilities to undo that. And then what we do is we basically are going to modify this face appearance. So you can see here, we're going to rename this from fuselage to right fuselage. And there's nothing special about the name right fuselage. Basically, we've renamed an appearance inside Onshape. And the cool thing here is now we can sync. So we have that workspace. We just changed that workspace, right? The broken branch workspace's state. And because, again, we kept that connectivity, we can then sync, which means we're going to take in the new status, the new state of that workspace. So when this import happens, you're going to see two things. One, we'll have no warnings anymore in the top right because we fixed those in Onshape and we've synced with the current state of the Onshape branch. And two, we have this tag, which actually is denoting the surfaces. So we renamed it to right fuselage. You can see it's called right fuselage. We already had a wings tag. And that is uniquely identifying surfaces in that CAD, which allows us then to script based on those unique surfaces, even if they change in the geometry. So that is a bit of how the integration works. And it's actually quite powerful. So what we just showed, because it's kind of easier to demonstrate, is in the UI. But we have the exact same functionalities available through our SDK as well, which again kind of allows that kind of flexibility and adaptation to whatever you kind of need to maximize your workflow and really get to maximal efficiency. So now we're going to talk a little bit about the shift-wing model and kind of use that as a baseline for kind of what Physics AI can do for you and how we can actually embed it inside your workflow, which we'll show in the next stage. But essentially, we used Onshape in partnership. They're very nice to partner with us and help us generate this data set. But we have that shift-wing model I just showed. We have all those variables in that variable studio, and we changed 7 of them. So aspect ratio, which I showed before in the imports, you can see here in the video on the right here, we're actually changing these things as we're talking about them. And you can see there's actually quite substantial deformations changing as we move these parameters from between the min and max range. And these are modifications in the variable studio. You could also do such a thing with configurations and generate these unique geometries. But again, Onshape was very nice to partner with us to be able to do this. But you can see we generated quite a bit of data, and there's quite a bit of change in the geometry here. And the impressive thing is both Onshape and Luminary remained robust to these geometry changes, which allows us to actually generate a very large data set. And by large, I mean we simulated 22,000 samples in about a month. So that means 22,000 unique simulations, many of which had unique geometries in those as well. And then also changing Mach numbers from 0.5 to 0.85. The interesting thing there is we're transitioning from transonic or from subsonic to transonic, so you get a bit different interesting physics there. And then also with very minimal human interaction, this was done all through the Luminary SDK and our integration to Onshape. So the key thing here is, how can we generate this data? How can we remain robust? We showed a bit of the sweep of the parameters we changed in the geometry. The other very important thing is we need to have an independence from the geometry to actually perform accurate simulations. And by that, I mean, in the typical simulation workflow, when you change that geometry, you're going to then have to worry about how do I mesh this thing? How do I get a good simulation of this? How many cells do I need in the boundary layer? And we've at Luminary have really kind of removed all those questions by having what we call Luminary Mesh Adaptation, LMA, which is a really, really fancy mesh adaptation that's highly specialized for these kinds of problems. But the key thing here is the input to get an entire simulation that you can trust for accuracy is exactly one number, which is just the number of cells you want to have in your final simulation. In this case, for shift wing, 30 million. And that is the only input you need. And after that, you can be confident that we're going to resolve the geometry correctly, that we're pulling in from Onshape, that we're going to resolve the flow physics correctly, because we're going to exactly mesh and adapt to that solution for every single one of those 22,000 samples I showed in that data set. And this is what really lets you work at scale, because you don't need to worry about how do I mesh this geometry, that geometry, this geometry for 20,000 samples, which really doesn't let you scale to the amount of data you really need to take advantage of Physics AI. So a single simulation in this case takes 1.5 hours. We're actually working on improving that speed. But the important thing here is, again, we're in the cloud, so you can actually run these in parallel. So you're not talking about 22,000 times 1.5 hours and taking years to do this. You can actually do it much, much, much more quickly. And as I said before, really the benefit there is Luminary's worked very hard to automate this inner loop. So how do we go from a geometry to a simulation we can trust without having to worry about tons of man hours, expertise, and carefully crafted experience over the years? And that starts from importing geometries like this integration from Onshape, and then having some light features. So you don't need to worry about polluting your Onshape CAD document with adding far fields, for instance, or symmetry walls or those kinds of things. We can handle those small things in Luminary itself. So you can actually just worry about making the CAD the model you care about, and then do those kind of CFD simulation specific things inside Luminary. And then as Joe mentioned, we have all kinds of AI infused to both do physics AI, but also to help you set up these cases. So we have AI assistants in the UI. We have an embedded hosted notebook like Jupyter Notebooks actually on the Luminary website. And we also have an MCP if you have your own IDE you like to use, or your own, you prefer using Claude Code or something like that, that you can connect and actually get information about Luminary and help drive those changes. And then the couple of big things here about doing these training data sets at scale is that, as Joe mentioned again, we're fully GPU native solvers built from the ground up over years and extremely specialized expertise from people we've hired that lets us really do these things extremely quickly, extremely accurately, with very limited user input and with very high robustness. And that lets you kind of just set it and forget it in these flows. So, if you're assigning those tags, like I mentioned before, where you can identify the wing, you can identify the fuselage, you can identify the far field, the same script's going to work for you over and over, and you can be confident those results are going to be quick and accurate. And then we also have data processing. We have a native visualizer I'll actually show in a little bit, and all kind of things you'd expect for both a cloud native platform as well as a simulation platform. And again, infused entirely with physics AI. So just to quickly talk about, if it's worth doing these models, if you can actually trust these. So we're comparing here to standard surrogate models. So basically, if you can predict lift and drag, giving those list of variable studio parameters, for instance, how can we do compared to that? And you can see Domino, which is the model we're using. It's inherited from NVIDIA, but we've enhanced it quite a bit. Does quite well and actually outpredicts, with more accuracy, the lift and drag in this case than these scalar surrogate models. But Domino does two really cool things that actually makes it way better than these surrogate models, even if it was just as accurate. And that is that it can predict full flow fields. So here we're showing CP. So you can imagine just the pressure flow field over this. And this is especially important if you have other considerations. Maybe you don't just care about lift and drag, but you want to post-process this into other things. This gets you actually a lot closer to a real, replacement for simulation beyond just getting a couple scalar numbers that you care about. And the other cool thing here is if you are, for instance, like the CFD guy at your company, but you have a whole mess of people that do thermal, that do loads, that do other parts of your engineering workflow, you can give them this full field, right? If I give them a full pressure field and someone wants to take it and compute a load, they can. But instead of running the CFD analysis, that again took about an hour and a half, and that's extremely quick because of how much we focused on that. This physics AI prediction takes about 5 seconds. So, you can even just give them the workflow themselves. They can click a button, they can get that result and calculate the loads that they want. The other really cool thing here is the only input for the geometry into Domino is the STL. So if you then throw away the parameterization you have and you start making these things in all kinds of weird ways, as long as it looks a bit like the plane you were simulating before that's in your training data, you're good to go. You don't need to worry about, I'm kind of shoehorned into this variable studio or the exact parameterization I chose before. If I wanted to add new parameters in variable studio and generate new geometry, that is completely fine. You're not going to break the model. And the last thing to point out here is you can see here on the left, the full fidelity CFD looks very similar to the physics AI prediction on the right. And what I want to point out, in case you haven't read the title, this is the worst case accuracy for CP. So you can see this looks quite good. You can see how sharp these edges are. That is because of our mesh adaptation. So that was no user worried about meshing this, that we just directly focused on capturing the solution automatically for you. But you can see it looks very close to physics AI prediction. And that is the worst case scenario. So if we look at actually looking over the entire validation set of this, you can see kind of as an R squared. So what we predicted here, or what we calculated from the simulations, what we predicted from physics AI, it lays almost exactly on this ideal perfect prediction line, meaning that it almost exactly recurred the results that we expected. And an important thing to point out here is the CFD results we also thoroughly vetted. We're not trying to use physics AI to match garbage. We did a lot of work matching what looks like an NASA CRM, looking at those physics, making sure they're accurate before we went ahead and actually trained this model. So you can trust these results you're getting. And if you thought this looked good in any way, trust that everything else you're going to do inference on will look better. So just to quickly wrap up on the models aspect there, we also have other shift models. Today we talked about shift wing, which is done again in partnership with Onshape. We also have shift SUV for kind of if you're more interested in automotive and car. And we're also focusing on rolling out many more of these models over the next year. So I would encourage you, if you're at all interested in this, to go to luminarycloud.com/models and bookmark that and check in. And also touch base with us if you want to be kind of kept in the loop on what we're developing. And also reach out if you think you have an idea for what would be very useful for your industry as far as these shift models go. And then just to quickly wrap up, I want to kind of show very, very quickly why this is useful. So right now we are formally a connected cloud app in Onshape. We can import geometry. We don't import anything back in. We're not embedded directly into the Part Studio, for instance. But we are moving towards a world where we're an integrated cloud app. And what this means is you'll have actual Luminary access inside Onshape itself. So we can perform inference, like I talked about before, in about 4 to 6 seconds on the shift wing. So if we have this branch we had before, let's say we're designing this plane, and I really care about what the physics looks like there. So I want some quick input on what the physics is going to look like for this. What I can do is I can go to the App Store. I could, once this is publicly released, go to the public Luminary one with a nice picture. But for now, we'll go to the private one just so I can show this functionality. What this is going to do is this is going to present a Luminary option inside your Part Studio itself. So here you can see on the right of this video, there's a little Luminary icon now. So we're going to hide the version thing just so you get a bit more room. And if you click this, you'll see now it says running inference. And what this is going to do is it's actually going to run inference on what you're currently looking at in your Part Studio and directly present it next to you in your Onshape window. So you can directly look at, for instance, in this case, the pressure field of this part that you actually are actively designing. And I'll skip ahead a little bit to save time. But the key thing here is it's our full LC-Viz, what we call LC-Viz, which is our embedded viewer inside Luminary. So you get access to every single feature you have there, including making things like slices and clips. The really cool thing here is we can go into the instance of variable studio again. We can change the aspect ratio just to make it obvious again. You'll see that if we skip forward a little bit, we'll have the regeneration as you expect in Onshape. We're also actively performing the inference as Onshape's doing that regeneration. So again, we immediately get the physics results for that exact thing we're looking at in the Part Studio. And just the last thing I want to mention, so you can zoom in and look at things, you can match the view over there. The last thing I want to mention is this is not, again, related in any way to the actual parameters that are set up in that variable studio. So we can go into the fuselage as we do here, and we can make a change, for instance, to the fillet. So we're making a discrete change, not related at all to those parameters we had before. This is going to lead to a regeneration that actually effectively removes it. And you can see here on the bottom, the junction between the wings and the fuselage is kind of removed because we did that discrete change to the fuselage feature. But again, we pick that up and the inference works. And that's because we're not tied to like the scalar circuit models usually are to actual input parameters. We are looking at the actual geometry embedded into a latent space for that STL. Just then, lastly, I mentioned this is not a scalar surrogate. We can't just give you lift and drag, but I should also mention we can still give you lift and drag. We do understand that scalar quantities of interest like mass flow rate, lift, drag, other kinds of things are important quantities, and that we can still expose those as well as this full field information that you can use then to drive your engineering workflow. And instead of performing a simulation, even if it is fully automated in about an hour, you can get physics inference results in about 5 or 6 seconds. So with that, I think we're going to open it up for questions. I hope you all have enjoyed the talk. I'm very excited to see what kind of questions you guys have. And if you are interested in this, I hope you do touch base with us. And just some quick contact information as well. We'll just leave it on the board.
Thanks, Rob. Thanks, Joe. I mean, impressive stuff. I feel like at Onshape, we always talk about the pace of innovation and cutting down these loops between design changes and getting physics feedback is just going to really speed up things for our customer base. So really exciting stuff. Decent amount of questions in the chat. Please feel free to drop some more. But there's one question about just what CFD solver you use. That is a Luminary proprietary solver you guys are using?
Yes, that's a great question. So unlike a lot of our competitors that base their stuff on open source, mostly OpenFOAM, we painstakingly built this solver over about, I guess as long as the company's been around, so about 6 years now. And it's fully GPU native, custom, built on CUDA. We currently run on H100s. We always try to stay on cutting edge hardware. So we put a lot of effort into making it this robust and this fast, and I think it shows.
And then in terms of types of physics, just CFD at the moment, or thermal or other things as well?
Yeah, another great question. Currently CFD and also thermal, and also the coupling between those, so conjugate heat transfer. So kind of the things Joe talked about before, we can do turbo machinery, we can do compressors, we can do external aero for automotive, for planes, as well as chip cooling, those kinds of things as well. And we're also looking to expand to more physics. So if we don't currently answer your needs, still let us know. You might be surprised how quickly we can kind of expose something for you.
Awesome.
Yeah, I'll also add to that. Sorry, Dan.
go
I'd
ahead.
also add that our physics AI platform supports a breadth of different physics, so you can build models on various different things. It could be structures, for example. But on the actual data generation side that we use to build this particular model, we were looking specifically at CFD.
Awesome. And just a note, we are at the bottom of the hour. We're going to hang on for a few more minutes and continue to answer some questions. But if you do have to drop, appreciate you joining, and we will definitely be sending everyone a recording. So maybe on that note, then Joe, a question here about analysis of fluid flow and heat transfer within an electronics enclosure.
Yeah, absolutely. That's certainly something that we could support. Happy to have a discussion with you about that. That's Mike.
Awesome.
It's Mike.
Yeah, and so it seems like there's a few different questions about specific industries here: fan design, fluid flow within electronics. It sounds like you can use maybe the Luminary solvers as they are, but for physics AI, would probably require some additional shift models or training.
That's right. Yeah, stay tuned on some of these things, and I'd say just generally, happy to discuss any of these different use cases with us. It's there are a breadth of things that we are looking at, and stay tuned for more shift models. I'll drop that hint as well.
Awesome. And then there's a question about what tool you're using to train the data. I'm not sure the exact context there. Do you guys have any comments there?
Sure, I can answer that one, I think. So we are using NVIDIA's Physics Nemo, specifically Domino, to perform the training and the inference. So that is the tool, but I will say we have wrapped it quite heavily and improved quite a bit of things on it. So we're actually faster than if you just pulled that down itself, because I understand it is open source. And also, we have quite a bit of expertise as well. So oftentimes, if you don't have a lot of in-house ML experience, we can kind of serve that need for you as well.
Awesome. There's one note about APIs here. I just want to make a quick comment from the Onshape side. So Luminary Cloud is a public app store partner. And so any work that you do with them is not going to count against anyone's API allocations within the Onshape environment. Awesome. Yeah, I mean, I think some more things rolling in about specific applications, but in my mind, I think we've covered most of the things. And any questions that we don't get to live here, we're going to follow up with offline. Once again, just appreciate everyone joining. Thank you to the Luminary team. Very excited about this collaboration, and looking forward to more things in the future.
Yeah, thank you so much.
Thanks, everybody.
Thanks, Dan. Thanks, everyone.